I'm going to be working out problem 3 from test 2. So we can see that a block of mass M is suspended motionless by a vertical rope in 3 identical springs as shown in the figure. Each spring has stiffness K and relaxed length L0. The spring from above forms an angle theta with the horizontal. The rope has an unknown tension, Earth's gravity points down. If you were to treat the 2 springs on the right of the block as a single spring, what is their effective spring stiffness, or K effective? Well, we can see that these 2 springs are parallel, they point in the same direction, and they're stretched equivalently. From this, we can see that K1, even though they have the same K, we're going to call it K1, is going to equal K2, where this can be K1 and this can be K2. Then we can see that our K effective is just going to equal K1 plus K2, which is going to equal 2K overall, since both K1 and K2 are described as K originally. Next, we're going to determine the magnitude of tension T in the rope if the upper string is stretched to a length of 3 L0. It will help you, alright, so first off, I would like to draw a free body diagram. I know it recommends to do it as well. So we're going to draw one here. It's going to be our body. So this is the force from the 2 springs originally, so we're going to call it force spring 2. This is talking about the upper spring, so I want to make that my spring 1. This is at an angle of the force of spring 1. That angle is going to be described as theta. And then I believe we're going to end up breaking this down into x and y components, so I'm just already going to go ahead and say that this is my sine, and this is my cosine, and this is obviously going to be our force of tension from the rope above. This is going to be our force due to gravity. So, we know from the free body diagram described above that it is motionless. And what that means is that if it's motionless, our F net equals 0 in both the x and the y direction. So this is asking the tension of the rope. The tension here, as we can see, is only in the y direction. There's no x direction components. So we can look at F net y and see that F net y is going to equal 0. And then we can look at all of the factors that go into the y component. We can see that it's obviously going to include the tension, it's going to include the force of gravity, and then it's going to include our force of spring 1, but only in the sine area. So what we can do is we can see that the force of tension is going to be a positive. It's pulling up on the y. Force of gravity is pulling down, so we're going to go ahead and do minus mg. And then our force of spring 1 is also pulling up, so it's going to be plus force of spring 1 in the y direction, which is going to be times our times our sine of theta. Then we can find that force of spring 1 is going to be times sine is going to equal our K times our 3 L0 as described above minus our original L0 times sine of theta. We're just multiplying the sines here and here, making sure it's equal on both sides. And from this we can find this whole thing is equal to 2 L0 sine of theta times K. And we can see that our tension is equal to mg minus, well, let me look back up here, mg minus r2 L0 sine of theta times K. Alright, and just so you know, this is what is inside the sine, the K is outside. Next we're going to look at the force exerted by the horizontal springs. I would also draw the free body diagram here again, just to help me out a little bit more. However, this time I'm only going to label this one, sorry, this is spring 2, not 1. And then I'll add my theta. So, what we're going to do for this one is we know that it's motionless, so our F net in the x component is still equal to 0, and we can see that the only thing acting in the x direction is our force of sine 2, or sorry, our spring force 1 and our spring force 2. So we can see that, sorry, let me write a little bit better here. F net x equals 0 equals force of spring 1 in the x direction plus the entirety of force of spring 2 since it is entirely in the x direction. Now we're going to see that our force of spring 1 is pointing in the negative x direction. It's in this quadrant and it's heading towards this direction. So we're going to have to make sure that this is a negative. So if we plug it back in, negative force of spring 1 times cosine theta, because it's the direction that it's only in the x, not the y. Y was sine, x was cosine, plus our force of spring 2. And if we plug everything back in like we did originally on the other problem, we can see that the force of spring 2 is equal to 2 L naught times k times cosine of theta. Now we can see that in our diagram, if these springs are pulling in this direction and our rope of our original diagram is completely straight, then we can reason that if it's pulling in this direction, it has to be pulling some in this direction in order for it to counteract each other. So it's pulling in this, the block is being pulled in this direction, the spring is being pulled in this direction, because these have to equal each other and cancel out. So our spring is stretched. Now we have to find out the length of the horizontal springs. So we can reason that the force of spring 2 is going to equal our negative k effective that we found in the first part times, so the value of L minus L naught times L hat. We know that our L hat was found to be negative 1, 0, 0 because it is pulling the spring in the negative x direction and in no other direction. So we can find that this entire thing is going to equal 2k times absolute value of L minus L naught. So this is our force of spring 2. And then we know that our force of spring 2 is going to be equal to our force of spring 1 times cosine, because they have to equal out and cancel out. So if we plug back in everything we found for this, it's going to be 2k to the value of L minus L naught equals 2k L naught times cosine of theta. Our 2k's cancel out. We're left with absolute value of L minus L naught. If we add this L naught back to both sides, we get L naught times cosine of theta plus L naught equals absolute value of L. A little bit of better vector notation there. I should have been doing that on more things. Which this is also just a little tangent, equal to L naught times cosine of theta plus 1. Thank you for your time.